Hi, I'm James Keane. I'm the lead scientist at JPL for the Endurance mission concept, and I'm going to give you a little status update about this concept. So, click the big giant button. Okay. So what is Endurance, if you're unaware? Endurance was a new mission concept developed in the most recent Planetary Science and Astrobiology Decadal Survey. And it is, in short, a mission concept for a large, well-equipped rover to traverse 2,000 kilometers across the South Pole-Aitken Basin on the far side of the moon, acquire a large amount of samples, and deliver those samples to Artemis astronauts. The concept study report was made public alongside the Decadal Survey. You can take a photo of the QR codes here to get these different documents. They're both massive 700-page things, but there's a lot of good details in there, and if you want to learn more about the concept, that's the first place you should go. So where is this concept going? It's going to the far side of the moon. This is a synthetic view of the far side of the moon, and you can't really tell it, but South Pole-Aitken Basin really takes over the entire southern far side, and you really see it when you start looking at topography data sets. So this is LOLA topography. This basin is enormous. It's over 2,000 kilometers across. It's extremely deep. And it is the largest and oldest impact basin that everyone agrees is an impact basin on the moon. So as I said, it's the largest and oldest, and it was formed in a big giant explosion. So this is a 3D ICL simulation showing the hypothesized formation of the basin from an oblique impact. And this is really interesting, not only because everyone loves explosions, but this would have excavated material from deep within the moon, including the lower crust and potentially the mantle, exposing it on the surface for us to sample. So this is a natural borehole into the interior of a rocky world. I'm a planetary geophysicist, which is interesting to headline a sample return session, but I get really excited about impact basins across the solar system, and SPA is actually the most accessible mega basin in our solar system, and I'm defining a mega basin as something sort of the scale of the planet itself. These things happen on almost every world, and they reshape those planets and moons in ways that we don't fully understand, be it big giant basins like Borealis on Mars or Sputnik Planitia on Pluto. But of course, one of the biggest, most important aspects of SPA is that it is the oldest impact basin on the moon. And the exact age is uncertain. It's one of the big goals of this mission, but it likely formed around 4 billion years ago or so, plus or minus several hundred million years, which is an epoch of time that is not preserved well on the Earth. It predates all of our Apollo samples. It would predate the Perseverance samples. And this is a really important epoch to go study because it records the environment of the Earth-Moon system at the time that life was first emerging on the Earth. It may hold records of the giant planets migrating around in the early solar system. And these are things that we just cannot access any other way. So going back to this map of the moon, SPA sample return has been priority for a very long time, basically as long as we've known that the basin exists. But one of the big challenges is that this is a very diverse basin, and it's hard to know exactly where to go to definitively answer all the science questions that exist. So for example, if you want to date SPA, there are lots of ideas about where you might want to go to do that. One idea is to go to the middle of the basin and grab a hypothesized impact melt. If you want to look at late heavy bombardment and giant planets migrating around, then you actually want to go to some of the younger basins that superpose SPA, shown here in cyan. If you want to look for mantle material, then you go to yet different locations. Here I'm using thorium as a tracer for mantle material. If you want to learn what makes the near side, far side of the moon so different, one thing you want to look at is the volcanism on the moon and what it might be different in SPA. Here it's shown in red for Mare deposits. And so you can see there's not a single place you can go and know for certain you've gotten all the science answers that you want. And Chang'e 6 and Artemis missions, they're going to go to certain locations in or near SPA, and they'll undoubtedly make major contributions, but we are unlikely to completely address all the outstanding questions for SPA. Endurance basically gets around all this by having extreme mobility, the capability to drive 2,000 kilometers and go everywhere that you would want to go to get the samples that you need. So endurance, this is an artist's rendering of the concept, is really a new way to explore. We do rovers on other worlds, most notably Mars, but this is just so vastly different in the scope that it would represent a dramatic change in how we do planetary exploration. For example, endurance in the original concept study baselined a sample capability of 100 kilograms. So that's more comparable to things like late stage Apollo missions than it is to traditional robotic sample return missions. So there you can see it compared to all these things. And most robotic sample return missions, even for the moon, are down in the single-digit kilogram values. And then for distance, it just blows everything else out of the water. The longest we've ever driven on another planet is with Opportunity at 45 kilometers. Endurance does quite a bit more. So this is a huge difference. To put this to scale, here's a little view of Washington, D.C. For an Artemis mission, an early Artemis mission, the astronauts might be able to walk about 2 kilometers away from their lander. So they could go from the Washington Monument to NASA headquarters. Endurance is like going from DC to Chicago through the Appalachians, off-road, with no GPS. So it's very different. To amplify this even more, you can imagine the different scales you have to think about. So on Earth, you have roads, you have GPS, you have lovely street view that can provide you centimeter scale imagery ahead of time. You have none of that on the moon. And importantly, if your self-driving taxi gets stuck because it drove into wet cement, which is the top right image, you can have people come get you out. If you get stuck with a rover on the far side of the moon, you are stuck. So I show poor Lunar here, which got dust on its radiator and died.
3 minutes.
Okay, so this concept is ambitious, but it builds on a lot of work that's been done for Mars and actually a lot of the autonomy that we currently do with Perseverance and Curiosity. To do this drive, you have to be able to drive autonomously for long distances at top speeds of about 1 kilometer per hour, which is very slow by human standards, but very fast for a rover. And I'm actually going to skip the details of this to get to the cool bits, which is we've started demonstrating these capabilities on Earth using both simulation and physical test platforms. So starting with the simulations, we've actually been, at JPL, been building computational simulations of the rover. So this is a full Terra mechanics mobility simulation. It does full rendering of the lunar surface. This is taking LRO data and then we upscale it based on what we expect on the surface of the moon. It creates synthetic images and then we run autonomy pipelines on this data and evaluate how well the rover would be able to do this drive. Critically, Endurance would have to drive it both day and night, so you can see it sort of simulating a day-night cycle driving through this crater. Now, the real cool one is we've actually taken this autonomy stack and put it on one of our rovers. So this is the Athena rover. It was actually one of the test beds for the MER rovers, Spirit and Opportunity. And so it's not quite the same mobility system as Endurance, but it's a great test platform to do sort of quick demonstrations. And so this rover right now on the video is driving itself between 2 predetermined waypoints. It is doing this at Pasadena night, which is not lunar night, using a flash system. It on board calculates, identifies hazards, maps out its traverse, adjusts the traverse based on hazards, and it's actually driving. It's actually exceeding our endurance requirement. It's driving at endurance speeds. Since this is sort of a half-scale rover, it's driving about half speed, so that's proportional. Finally, we actually have just finished construction of an earnest prototype. This is a half-scale model of Endurance, which the engineers, they picked this name without me. It's Ernest, after Ernest Shackleton. And so in the very near future, we'll be deploying this rover in and around Pasadena to do some test operations. So finally, last slide. There's a lot of things on here, but the most important is to keep your eye out for the forthcoming science definition team for a South Pole-Aitken Basin sample return and exploration concept, which was effectively endurance. So please participate. And with that, thank you very much.